Hello class, welcome to this video on AP Statistics 6.1, 6.2 assessment. Let's go over one of the versions of the test here. So first one, the following table shows the probability distribution for the number of books a student typically buys at the annual book fair held at an elementary school. Let the random variable B represent the number of books a student buys at the next book fair. What is the expected value of B? Okay, so we're talking about expected value. Here they're talking about the mean, right? So they're talking about the mean of B. Now remember that the formula for, in general, the formula for the expected value of a random variable is in your formula sheet. And it is the sum of the values for xi times the probability of xi. So in this case, we're going to do that for B here, right? So this is your random variable here, and then this is your probability of that random variable. And these are your BIs, right? B1, B2, and these are your probabilities. So we got 0 times 0.35 plus 1 times 0.20 ... all the way to 7 times 0.01. And of course you can do this on the graphing calculator, which I will show you how to do that in just a second, or how to remind you of how to do that. And we get our answer here. So the answer is going to be 1.79. So the answer is C. I'll show you how to do this on a calculator. Okay, so here's how to do it on the graphing calculator. So when you have it, remember you want to make sure that you hit, stat, and then go edit, and then you type in your numbers. So 0 to 7 on one list, and then you type in your probabilities on the other list. So here they are already. Then you go back to stat, and then you go to calculate one variable statistics. Make sure you got L1, L2. And then you can calculate it, and that's what we got earlier, 1.79 for our mean. Okay, so let's look at number 2. A raffle for a charity fundraiser is being planned. Each of 2,000 raffle tickets will be sold for $1. The holders of 32 winning tickets will win a prize. The table shows the prize values and a number of prizes for each value. The random variable W represents the value of the prize won for a single ticket minus the cost of the ticket. What is the expected value of V? All right, so let's set up a probability distribution for this, right? So we have W is the random variable, and then we got P of W. Okay, so I'm gonna say W equals little w. Okay, so we want we have the possibility of getting no prize, but then paying for the cost of the ticket, right? And each of the cost of the tickets are $1 each. So remember, it's a prize won minus the cost of the ticket. Now, if they didn't win a prize, then that's $0 minus the cost of the ticket. So that's negative $1, right? And then what's the probability of that? Well, there's 32 winners here in total, so that means it's the rest of the 2,000, right? So it's 1,900. Let's subtract 2,000 minus 32. It's 1,968 out of 2,000. And then we got, okay, so now if we win the $25 prize, then we end up getting $24 profit, I guess, if you would say, minus the cost of the ticket. And that's 20 out of 2,000. And then we got $10, which is $49, or I'm sorry, $10, $50, so $49, so 50 minus 1, but then there's 10 tickets out of 2,000. And then the last one is $300 that you win, so $299 because you're paying the ticket. And then we got 2 out of 2,000. All right, so that's your probability distribution, and then we could just calculate the expected value, right? So we got mu W equals negative 1 times 1968 out of 2,000 plus ... plus 299 times 2 out of 2,000. Now, it doesn't make sense for you to do the dot to dot unless you actually show this table, right? Because if you don't show this table, then you're gonna have to show your numbers, all your numbers, because we want to know exactly how you actually got your calculation from UW. But since there's a table here, it's very clear what we're referring to with the dot dot dot. So that's something to keep in mind. All right, so let's see here. We have our answer, so we can calculate this, and if we do this, we get negative 0.20. So you're going to owe 20 cents on average. Okay, all right, so that's our final answer is B. All right, so number 3. At a large regional collegiate women's swim meet, an official records the time it takes each swimmer to swim 100 meters for all swimmers who compete in only one stroke category. The following table shows the mean times and corresponding standard deviations for the collegiate women at the swim meet. Okay, so we have the stroke categories, the mean times, and then the standard deviations. All right, so we can call this, for example, mu1, mu2, mu3, mu4, and then sigma 1, sigma 2, sigma 3, sigma 4, okay? For each of the 4 stroke categories, consider a random variable representing the time of randomly selected swimmer in that category. What is the standard deviation of the sum of the 4 random variables? So we want the sum of the 4 random variables. Let's call that sigma t, okay? Let's call t is the total of the times, right? So we'll say t is x1 plus x2 plus x3 plus, I guess I should have called this mu x1, not mu1. Sorry about that. Mu x1, because you need a variable, right? So mu x2, mu x3, mu x4, sigma x1, x2, x3, and x4. Okay, so... And then, so let's put x4 here. All right, so then the sigma t, to do the standard deviation, remember that you cannot simply add the standard deviations. You have to, for this particular example, well, for any time you're combining standard deviations for variables, you actually have to combine the variances and then take the square root of the variances. So it's going to be sigma squared x1 plus sigma squared x2 plus sigma squared x3 plus sigma squared x4. Okay, so this is how you combine the standard deviations. All right, so we got square root of 0.70 squared plus 0.92 squared plus 0.94 squared plus 0.76 squared. All right, and if you do that, you get B, 1.67 seconds. All right, so we'll look at the next one. Number 4, a player pays $15 to play a game in which a chip is randomly selected from a bag of chips. The bag contains 10 red chips, 4 blue chips, and 6 yellow chips. The player wins $5 if a red chip is selected, $10 if a blue chip is selected, and $20 if a yellow is selected. Let the random variable x represent the amount 1 from the collection of the chip. Let random variable w represent the total amount 1, where w is equal to x minus 15. What is the mean of w? All right, well, first off, we have to use this information here. And if we want the mean of w, so the mean of w is just the mean of x minus 15, okay? So that's the transformation there. And to find x, well, we're gonna have to set up a probability distribution. So it says we have 10 red chips, 4 chips, and 6 yellows. So that's out of 20. So we know all these are out of 20. And then it says it says there are 10 red chips. So let's do that. 10 red chips. We have 4 blue chips and then 6 yellow. And if it says we win $5 if a red chip is selected, but we pay $15 to play the game. So really it's, we pay $15, and then we get $5. So that's negative $10. We get $10 if a blue chip is selected, right? So then that's, we pay $15, but we get $10. So that's negative $5. And then $20 if a yellow chip is selected. So that's, we make $5 basically. All right, and those are our options. And so we can find the mu for x there. So the mu for x is going to be -10 times 10 out of 20 plus -5 times 4 out of 20 plus 5 times 6 out of 20. And oops, I just realized that this is not x, this is w. So this is x minus 15. So this is actually w, sorry, not x. Let me change this to w. This is mu w. All right, because I included the fact that it's minus 15 because you pay $15. So, all right, so this is w. If you were to set up x, it would just be $5, $10, and $20. So yeah, we could just calculate it here. So, so again, just to be clear, if I set up as x, this would be $5 if you win, $10 if you get blue. Sorry, $5 if you get red, $10 if you get blue, $20 if you get yellow. With these probabilities, of course, the same probabilities. Okay, and then you would calculate the mu x there. And then if you calculate the mu x, you will get somewhere, you will get about 9, let me see, 1150, around there. And then you subtract that from 15, right? And you would get mu w equals that minus 15 is -4.50, something like that. But in any case, if you did this, you would still get the same answer, right? -4.50, if you calculate it directly from there. All right, so the answer is C. All right, so number 5 says the distribution of random variable R has a mean of 10 and standard deviation of 4. The distribution of random variable S has a mean of 7 and standard deviation 3. If R and S are independent, then what are the mean and standard deviation of the distribution R minus S? Okay. All right. So the mean of R minus S is the mean of R minus the mean of S. Okay. And then the standard deviation of R minus S is the square root of the sum of sigma squared R plus sigma squared S. All right. And that is what you got to know. And so we got mean of R is 10, and then mean of S is 7, so it's got to be 3. And then this says that the standard deviation of R is 4, so we got 4 squared, and then the standard deviation of S is 3, so 3 squared. And you can calculate your answer there. And so the answer is going to be, well, 3 squared plus 4 squared is going to be square root of 25, and square root of 25 is 5. Okay, so the answer is B. All right, number 6, in a certain game, a fair die is rolled and a player gains 20 points if the die shows a 6. If the die does not show a 6, the player loses 3 points. If the die were to be rolled 100 times, what would be the expected total gain or loss for the player? Okay, so let's set up our table. So we got, let's say x is the number of point, the total, or the number of points, right? So we get, so it says a die shows a 6 or not a 6, okay? So that means we can lose 3 points, right? And it says, yeah, fair die is rolled and it gains 20 points if the die shows a 6. Okay, so then we can get 20 points for there, okay? And so in this case, we get minus 3 points if we get or plus 20 points if we get a 6, and then if we don't, we get 5 out of 6 chance of losing 3 points, right? On a standard die. And then what we want is, okay, so let's calculate the mu x for this, right? Which is -3 times 5 out of 6 plus 20 times 1 out of 6. So let's calculate that. In that case, this is -15 out of 6 plus 20 out of 6 which is 5 out of 6, or 0.833. I'm just going to leave it as 5 out of 6. So now what we want, okay, it says you're rolling the die 100 times. So really what you're doing is you're doing this 100 times. So you're timesing all this result by 100, right? So you're doing 100x for your random variable. And so the average of that is just 100 mu x, okay? And multiply your result by 100. So we got 100 times 5 out of 6, which is 500 out of 6. Okay, and let's divide that, and we get a gain of about 83 points right here. So this is about 83.3. So the answer is C. All right, so number 7, at a certain company, loan agents are paid based on the number of loans they close in a day. Based on company records, the number of loans X that a randomly selected loan agent closes on a randomly selected day has a probability distribution below. At the company, the daily salary of a loan agent is $150 plus $50 per loan closed. Let Y equals the amount of money made by a randomly selected loan agent on a randomly selected day. Which of the following statements is not true? So first off, it says Y represent the amount of money made by a randomly selected loan agent on a randomly selected day. So that means that they're saying that the random variable Y is 150 plus 50 times the number of loans, and the number of loans is X, right? Capital X. All right, so and let's see. It says the mean of X is less than the mean of Y. Is that true? So we need to calculate mu X and mu Y, right? But if you think about it, I mean, if you're trying to find mu X and then you're trying to find mu Y, well, if you're looking for mu Y, well, if you know your transformations, we know that the mu Y is going to be bigger because mu Y is 150 plus 50 mu X, because we have the 150 plus, then we have 50 times X, and so it's going to be 50 times mu X. So we can clearly see that this is greater than mu X, and so it cannot be A, right? Or rather, I should say it can be A, and so therefore it's not the answer, right? So because it says that X is less than the mu of X is less than mu of Y. Well, that's true. So therefore that's not the answer, right? Because we're looking for not true. Then the standard deviation of Y is approximately 71. Okay, so let's do that. So standard deviation of Y, let's do that over here. So standard deviation of Y. How do we calculate the standard deviation? What's the square root of the sum of your variable? In this case, we're talking about Y. So it's Y minus mu Y squared times, the square root's really big here, times the probability of little y. And then this is yi, so we just put little i's there. All right, so you can calculate that way. And this is a perfect question for you to just calculate this using the calculator. So let's show you how to do that. So we just do it on the calculator. Okay, so we're going to calculate this. So we're going to go to stat, edit, and then we type in the values. I've already typed in the values here. We go stat, edit, calc, and one variable stats, L1, L2. And we get 3.94 for mu x, and for the standard deviation, we get 1.41. So 3.94, 1.41. Okay, so 3.94, 4.41. Okay, so this is 3.94, and then sigma x is 1.41. All right, so in that case, we can, once we know mu x and sigma x, we can find mu y and sigma y. So let's see if the part B is right. The standard deviation of y is approximately 71. Well, the standard deviation of y, we can actually, since we know the standard deviation x, we can get the standard deviation of y. Okay, rather than using this formula, which the calculator already used for x, let's do this for y. Since we know the standard deviation of x is 1.41, and we know the transformation, we just have to multiply 50 Remember that addition does not affect the standard deviation, so the 150 doesn't affect anything. The 50 times, however, does. So we got to do 50 times sigma x. So it's 50 times 1.41. So if we calculate that, we get $70.50. So 70.5. So it's not, which is approximately $71, right? And so it cannot be B because it looks like B is right. Now let's do part C. The mean daily salary is greater than $350. So let's see if that's true. Well, we know that we can calculate this using the formula, right? So mu y is 150 plus 50 times mu x, which is 3.94. So we can just calculate that and see if we get that answer. All right, so if I do that, I get $347, which is less than $350. So it's not C, so the answer has to be C. Okay, so let's look at the next question. So let x represent the number on the face that lands up when a fair six-sided die number cubed is tossed. The expected value of x is 3.5, and the standard deviation of x is approximately 1.708. Okay, so we know the expected value, and then the standard deviation. The two fair six-sided number cubes will be tossed, and the numbers appearing on the faces that land up will be added. Which of the following values is closest to the standard deviation of the resulting sum? All right, so we have basically x1 and x2, right, are the numbers on the two dies. And we want to do the standard deviation of that sum, okay? So the standard deviation of x1 plus x2, right? So it's a square root of sigma squared of the variance of x1 plus the variance of x2. All right, so we got the expected value. So now they said they give us the expected value, but we don't really need that because we have the standard deviation here of 1.708. So let's go 1.708 squared and then 1.708 squared. All right, and the answer here is 2.415 right here. So the answer is C. All right, so number 9. A company that makes fleece clothing uses fleece produced from 2 farms. Let the random variable x represent the weight of fleece produced by a sheep from Northern Farm. The distribution of x has mean of 1.41 pounds and standard deviation of 1.3 pounds. Okay. Let the random variable y represent the weight of fleece produced from Western Farm. Okay. Distribution of y has a mean of 6.7, standard deviation 0.5. Assume x and y are independent. Let w equal to the total weight of fleece from 10 randomly selected sheep from Northern Farm and 15 randomly selected sheep from Western Farm. Which of the following is the standard deviation in pounds of w? Okay, so I want to make a correction here. It says x and y are independent, and also it says x is the weight of fleece produced by a sheep. So a single sheep. So it's for each sheep. That's the weight of x. So this expression is incorrect. So let me fix this here. All right. So let's go ahead and fix w real quick. So we're gonna say, okay, w1. So we're gonna call w1 is equal to w1 plus w2. All right. We'll call it, we'll just call it wx plus wy. Let's do that. Okay, because x is like the individual sheep, and w is the total weight of the sheep of the fleece from the different sheeps, right? So in other words, wx here is the weight of the sheeps for that farm, right? And so it's going to be x1 plus x2 plus x3 all the way to x10. Now the sheep are independent, so this is why this is important here. There's 10 sheep from the Northern Farm, and then for the other farm, it's y1 plus y2 plus y3 all the way to 15, the 15th y. All right, and this is what this represents. Okay, so each sheep is its own, I guess you could say, independent random variable, if you will. Okay, Okay, so then we can go back to this question. So let me adjust this. I apologize for that. So now we have, now for this, let's do this guy. So for sigma wx, right? For that part, that's going to be the square root of sigma squared x1 plus sigma squared x2 all the way to sigma squared x10, right? But remember that x is just a sheep, right? So it's not going to really make a difference if we have x1, x2, x3, because even though the sheep are independent, x is just the weight of a particular sheep. And we know that the standard deviation of each of the sheeps is the same, right? So the standard deviation of each sheep is 1.3 pounds, right? If you were to average out the sheeps, and that's the standard deviation. So this right here, that is your sigma x right there, which is the same as sigma x1, sigma x2. So really, you have 10 of these. So you have the square root of 10 sigma squareds, right? Because each of these is sigma squared x. And they're all the same. And so we have 10 of these. And so what we end up getting is that the sigma wx is just square root of 10 sigma squared x, which is the same thing as the square root of 10 sigma x. Okay, so this one is an interesting one when we set it up. Okay, so that is sigma wx. So let me just underline that. Now the same thing for sigma wy. Sigma wy similarly is going to be the square root of sigma squared y1 all the way to y15, right? But we know that they're all the same. They're all sigma y, and sigma y is 0.5, right? So let me put that as sigma y. And so it's going to be 15 of those. So it's going to end up being this, right? Square root of 15 times sigma y. All right, this is what we need. And then we can plug into this. So it's a square root of sigma wx squared plus sigma wy squared. And then when we plug it in, we get the square root of 10 sigma x squared plus the square root of 15 sigma y squared. All right, and just because I'm out of room, I'm going to put it over here. Actually, let's do it down here, or let's do it over here. So then we get square root of what's the square root of 10 squared? That's just 10. So it's 10 times sigma x squared. And then we get 15 sigma y squared. But we know that sigma x and sigma y are 1.3 and 0.5. So the answer has to be C. Okay, so that was a tricky one because the way I was about to do it, I was gonna get D, but it's incorrect. It's incorrect the way I was gonna do it before. We have to kind of think about it as, the whole, as this idea, right? Which has the square root in it to begin with. All right, so that's number 9. That was a tricky one. You just have to be careful with what they're asking for in that question. All right, so number 10, let random variable u represent the field goal percentage of shots made for players in a basketball league. The following table shows the probability distribution of the random variable u. Fatima claims that the distribution of u is uniform with a median of 0.4 field goal percentage. Is Fatima's claim supported by the table? All right, so the median, remember the median is the 50% mark. So what you have to do is just add these until you get to 50% or higher. So we got 0.10, add that to this. Okay, so that's going to be 0.55. So now we're at the 50% mark, right? So that means that that has to be the median. So she is correct in this regard. However, is it uniform? Well, if you were to quickly graph it, right, you can see you got 0.10, then you got 0.45, so really high. Then you got 0.30, so that's lower, and then you got 0.10 again, and then 0.05. And we can see from that graph that it's skewed to the right, so there's no way we're going to get something that's uniform. Definitely not that, right? Uniform would be the same anyways, right? So we already know that that's wrong. So we can see that it's skewed right with a median of 0.4. The answer is C. Okay, so let's do the free response here. So scroll down here. All right, so number one, 11 is all of Dave's customers are neighbors that have yards of about the same size. Dave charges a flat rate of $32 for mowing and trimming and $20 for just mowing. Based on experience, he determines that the probability that a randomly selected customer wants him to mow and trim the lawn is 0.85. The rest of his customers just want him to mow. Let C equals the amount Jacob charges a randomly selected customer. So make a table that shows the probability distribution of C. All right, so we got C is the charge, the amount of money so that he charges, right? So say C, and then we got the probability of getting a particular charge. And we have a couple options. We got $32 for mowing and trimming, and then we got $20 for just mowing, right? And it says there's a 0.85 chance of this happening, and then a 0.15 chance of that happening, because it has to add up to 100%. And those are the options, right? So that's it for part A. Part B, calculate and interpret the mean of C. So we got mu of C equals 32 times 0.85 plus 20 times 0.15. That's it. So that's going to be $30.20. And we want to interpret it, okay? So if many customers are randomly selected, the average charge would be about $30.20. Okay, so there's your interpretation. Remember, using the idea of if a lot of customers are randomly selected. So you need, you don't have to say many, but you say if a large amount of customers are randomly selected, average charge would be about $30.20, something like that. All right, calculate and interpret the standard deviation of C. Okay, so we got sigma C is equal to the square root, and then you have to take the we'll write out the formula just so you can see it. So it's Ci minus mu C times the probability of Ci. So we got the square root of the first charge. Oh, and we have to, I forgot to do the sum, so we got to sum that. All right, so we add them up. So we got, okay, so 32 minus mu C, which is $30.20 squared, times the probability is 0.85 plus 20 minus 0.15. Oh, I'm sorry, 20 minus 30/20 squared times 0.15. All right. And then we get our answer. So we'll just do that on the calculator. You should get about $4.28. All right, so let's interpret. If many customers are randomly selected, the amount charged will, on average or typically, vary from the mean of $30.20 by about $4.28. Okay, so there you go. And you can there's different ways to word it. I mean, you can say the amount charged will on average vary by about 428 from the mean of 3020. You know, there's a little bit of a flexibility in the wording, but for the most part, there's a way that you would word it. Number 12, a single toss of a fair coin results in either 0 or 1 head, each with probability of 1/2. Define h equals the number of heads obtained on a single toss. The mean of h is mu h is 0.5, and the standard deviation is sigma h is 0.5. Suppose you toss a fair coin 4 times. Define t equals the total number of heads obtained. Find the mean and standard deviation of t. Okay, so in other words, t is equal to h1 plus h2 plus h3 plus h4, right, for each coin toss. And so mu t is equal to mu h1 plus mu h2 plus mu h3 plus mu h4, which is the same thing, but each of these are the same. Each of these are mu h. So it's just 4 mu h, right? So we got 4 times 0.5 is 2. And then the standard deviation of t is standard deviation, well, let me just be clear. Let me just rewrite it as standard deviation of h1 plus h2 plus h3 plus h4, right? And remember, to do the standard deviation, you have to take the square root of those. But we know that each of those are the same. They're both sigma h, sigma squared h, or sigma h. So then you get basically 4 of them. And so really it's the square root of 4 times sigma h, okay? So sigma t is the square root of 4 sigma h, which is just 2 sigma h, okay? So then in this case, it's 2 times sigma h, which is 0.5, which is 1. Okay, so you gotta be careful, again, to avoid the mistake that some students make. So those are the answers, but be careful to avoid the mistake that you say that t is 4h, okay? That's not the random variable that you want here. Okay, so do not do this, all right? I just want to be clear. Because it's very tempting to just say that t is 4h, because, hey, they're all the same, right? This is a different type of variable. 4h is not the same as h1 plus h2 plus h3 plus h4. Okay, so because when you calculate the mean of this, right, you get 4 mu h, right? And then the mean of this is the mean of 4h, but then the mean of 4h, or the sigma of 4h, and the sigma of 4h is just 4 sigma h, right? And we know that that's not the case because for this problem, because it was actually 2 sigma h, not 4 sigma h. So do not do this. This is a something that you do not want to do. Okay. All right, so number 13. The time x it takes Professor Sawyer to drive to campus on a randomly selected day follows a distribution that is approximately normal with mean in 37 minutes. Okay, so we got the mean and then the standard deviation 3 minutes. After parking his car, it takes an additional 3 minutes to walk to his classroom and 2 minutes to start the computer. Then he is ready to begin class. Let t equals the total time it takes him to get to his classroom and be ready to begin class. Describe the shape, center, and variability of the probability distribution of t. Okay, so in this case, okay, it says, so the mean is 37 minutes. We got mu x equals 37 minutes. And then we got, of course, we got an additional 3 minutes to get to it and 2 minutes. And then t is the total time. So t is the random variable for the time it takes for him to drive to campus, which could be, on average of 37 minutes, but it could vary, right? It could be 40 minutes, 20 minutes, whatever, 25, whatever that time is, plus the time it takes to get to to walk to his classroom, and then 2 minutes to start the computer. So really, it's just x plus 5, right? That's what t is. And so mu t is mu of x plus 5, right? Which is the same thing as mu x plus 5. All right, that's that variable right here for mu t. So yeah, just add 5 to it. So mu t is equal to 37 plus 5, which is equal to 42 minutes. All right, so there's that one. And then if this is the random variable, then we're not doing anything to the standard deviation because we're just adding 5, which doesn't affect the standard deviation. So the standard deviation of that random variable is just sigma x. It doesn't really do anything, right? The plus 5 doesn't do anything, which is just, did they give us that? Yeah, they said the standard deviation is 3 minutes. Okay, so we got 42 minutes, 3 minutes. It doesn't do anything to that. And the shape is going to be the same here. It says it's approximately normal, so then the shape is going to be approximately normal as well. Because remember, these kind of transformations do not change the shape of the distribution. So we got those 3 answers. All right, so now we're in the last question. This is the question that probably maybe a lot of students struggled with. Let's take a look at it. So two 5-year-old girls, Elise and Jocelyn, have been training to run a 1-mile race. Elise's 1-mile time, A, is approximately normally distributed with a mean of 13.5 minutes. Okay, so we got Elise's mean time and standard deviation. And we got Jocelyn's 1-mile time is approximately normally, so they're both normally distributed. That's important to know there. With a mean of 12 minutes and a standard deviation of 1.5 minutes. Assuming A and J are independent random variables, what is the probability that Elise has a smaller time than Jocelyn in a 1-mile race on a randomly selected day? Okay, so we want the probability that Elise has a smaller time, right? So that means that Jocelyn's time has to be greater than Elise's, right? That's what we want to look for. So Elise is less than Jocelyn. So another way of saying this is that we want the difference between Elise and Jocelyn to be a negative quantity. We want it to be less than 0. Elise has a smaller time than Jocelyn. When I subtract Elise's time by Jocelyn when I subtract those 2 quantities, I should get the negative number. And let's call this random variable D for the difference, okay? We're going to call that D. And we want to find the probability that D is less than 0. Essentially, that's what we want to look for. Okay, now we can do this transformation because remember, this is a subtraction transformation. It does not affect the shape of the distribution. So we know that the shape of the distribution is going to be normal, right? So we know that the shape is approximately normal. Now, how do we get the distribution of this? Well, the distribution is going to be the mu for D and then the sigma for D, right? So we need to figure that out, okay? How do we get that? Well, the mu of D is the mu of A minus the mu of J. Okay, so it takes care of that. And then we know that the mean time for Elise is 13.5 minutes. And then the mean time for Jocelyn is 12 minutes because they told us those 2 things. And so we see that it's 1.5 minutes for the difference. Okay, so now we can do the standard deviation of that difference. Remember, the standard deviation follows the Pythagorean sum rule, okay? So it's the Pythagorean sum, right, of the 2 standard deviations. So you take the square root of the 2 variances, sigma A and sigma J, sigma squared J. All right, so we got the square root, and then we have Elise's time is 2.5 minutes squared, and then we got the other one is 1.5 squared. So when you do that, you get about 2.92 minutes. Okay, so now since we know it's approximately normal, right? With those two parameters, we can draw a normal distribution and this is going to represent the variable d, right? And so the mean of d is 2.92 or no, that's a standard deviation, I'm sorry. So the mean is 1.5, and then we're gonna add 2.92 and subtract 2.92. So let's get those numbers. So if I add 2.92, I got 4.42, add another 2.92, 7.34, and then 10.26. And then if I subtract negative 1.42, negative 4.34, negative 7.26. All right, so there you go. There's my standard deviation, or there's my normal distribution approximately. And we want to figure out the probability that D, remember we're looking for the probability that D is less than 0, right? So 0 is my value. So 0 is somewhere around here. And we want it to be less than that. So that to the left. Okay, so then we're gonna go ahead, we can use the, in order to calculate this, we can use normal CDF, right? So we can use normal CDF in order to do this. We can also use the value, calculate the Z score and then look up from the value from the table. I'm gonna do both ways for you guys, okay? So I'm gonna do the table and using technology. All right, so let's calculate the Z-score first. So if we want to calculate the Z-score, we get Z is equal to, remember, it's value minus mean divided by standard deviation, okay? So in this case, we get the value, in this case, the value is D, which is 0. And then the mean of D is 1.5, the standard deviation is 2.92. And when you calculate this, you get Z is negative 0.51. Then we can look up the probability that Z is less than that. Remember, the table gives us the area to the left of that. And then we can look it up from the table. All right, so let's look this up on the table here. See if we can look up the value. Okay, here we go. So we're gonna look up the value. So we're using our AP sheet here. So we get negative 0.51. You can see that over here. Negative 0.51. Then the value is 0.3050. All right. Okay. So now we know that the probability. And remember the table gives us the area to the left. So that's what we're looking for. So 0.0350. So I'm going to write that this is the same thing as the probability that Z is less than negative 0.51, which is 0.3050. Okay. Another way of doing this, remember, is using the on the calculator, the normal CDF function, right? So that's what we're going to do here. So we're going to show you that here. All right, so let's do that. Let's, well, we'll show you on the calculator, but let's write out the function first. So we get, let me do that over here, just so I have room. Okay, so we got normal CDF. We got our lower, which is, in this case, our lower is negative infinity, right? Or like a negative 1,000. I'm just going to do negative 10 to the 9th power. My upper is 0, right, for D. Okay. My mean is 1.5. And our standard deviation is, what's our standard deviation? Oh, 2.92. All right, so let's do this on the calculator. Again, so remember you want to hit second vars and go to normal CDF. You really are not going to be using the normal PDF. You're really going to be using normal CDF. All right, so we got normal CDF, and then we want this to be negative 10 to the 9th power. All right, so we want this to be, oops, I forgot, I didn't mean to do that, negative 10 to the 9th power. So we got really, you know, negative. And then the upper is 0, and then our mean is 1.5, and standard deviation was 2.92. All right, and then we get that, so we get 0.3037. All right, so we get 0.3037. Okay, so that's one way to do it. So either one of these would be appropriate. I will show you, this is how you would do it without standardization. If you want to do it with standardization, it will look, the only difference is the lower, so these are, the lower and upper are going to be the same. But the mean is going to be 0 if you standardize it, and the standard deviation is going to be, oh, I'm sorry, the upper is not going to be 0. The upper is going to be your z-score, which is negative 0.51. Okay, and then the mean is 0 and a standard deviation is 1. This is how you standardize it. When you standardize it, the mean is always 0 and the standard deviation is 1. But if you standardize it, I'm going to show you that you're going to actually get a more accurate answer. You're going to get something more in line with what we got here. So it's something to know, to keep in mind, that, you know, your answer is going to be off if you don't standardize it sometimes. And we're going to show you that here. Okay, so let's do that. Second vars. We got normal CDF, and this time we're going to standardize it. So we're going to use the z-score that we got here, negative 0.51, and then this is going to be 0 now, and this is going to be 1. And let's see how, so there you go. So you get something more in line with what we got before, 0.3050, and that's because you standardize it and use the z-score instead. So it's more closer to what we want. All right, so in this case, we got 0.3050. So I showed you with 3 ways: the z-score, and then with the calculator without standardization, and the calculator with standardization. All right, that's going to do it for the video, guys. Hope you found this useful and informative. As usual, I'll see you in the next one.